So now that we can think about a molecule in three dimensions, we want to start to think about how a molecule behaves, whether it is in a solution, in a compound by itself, or what does that look like? So let's think about electronegativities. If we remember the electronegativity trend, we see that it increases as you go across and it decreases as you go down. And so on the next slide, we'll go over it again. But one of the things we can think about is how does this affect molecules? Based on the electronegativity trend and a structural compound, we can draw a structure of HCl. This is a linear molecule. And this bond is polar. When we think about a 3D structure of water and CO2, both of these have bonds. So we have a CO and an OH. So this bond is polar, and this bond is polar. So we have two polar bonds. So let's think about, are these molecules polar? So we can draw a 3D structure of water, and I'm going to draw it a little differently than maybe we've been drawing it, but it's still the same. So we have this structure. So in this case, our two polar bonds go in this direction. So there are two polar bonds, and overall, they give you a polar molecule. And this is polar. The two polar bonds add together. And so when they add together, you can get a polar molecule. So let's think about CO2. It also has a carbon-oxygen bond, or this one has a carbon-oxygen bond. And the question is this going to be polar? So our Lewis dot structure or our Vesper structure, they have the same structure. Looks like this. So when we orient our polar bonds, it turns out that they point in opposite directions. So this is a nonpolar molecule. The two polar bonds cancel each other out. So we see these two bonds that pull equally hard in opposite direction. When we think about a polar bond, it is two atoms pulling like in a small tug of war between two items. In terms of both water and CO2, we're now thinking about different teams of bonds competing in a tug of war. So the arrangements, they can be very polar bonds that cancel each other out, or they can add together. You can also see in some cases where the arrangement of the polar bonds can cancel each other out to give you an overall polar molecule with a dipole moment. So the electronegativity trend is this. We see that it increases as you go this way, and it's going to decrease as you go this way. And it's important to note that the differential of 0 to 0.4, this is basically the chi1 minus chi2, where chi is the electronegativity. So whether it is covalent or polar can be calculated using this. So we can use these numbers to determine how polar or how nonpolar something is. And so we can use this to determine things. So if we look at these compounds, NH3, CH3Cl, and CCl. So the electronegativity values for these elements are found in this table. So we can actually start to look at these and determine which of these bonds are going to be polar. So let's start by asking that. NH, we're going to have a CH, we'll have a CCl. So these are the three bonds that we're going to see. So N minus H is a 0.7 polar. Carbon hydrogen, 0.4, kind of polar, but still on the border, and carbon chlorine is 0.5, and this is polar. So we'll call this non-polar. polar for carbon hydrogen. Although it is on the borderline, it is most often assumed to be nonpolar. So the question asks which of these are polar. So most of these have a polar bond. So how can we figure out what is polar and what is not? So we need to look at the 3D structure. So let's draw the 3D structure for each of these. So we have NH3, which is going to look like this. That's not right. We have a lone pair. We have our 3 hydrogens. We have a carbon, 1 chlorine, and our base geometry looks like this. So we're going to put the chlorine anywhere we'd like. I'm going to put it up here at the top. That's not a chlorine. That is. Then we have 3 hydrogens, and let's look at carbon tetrachloride. I forgot my lone pairs, and it has the same base geometry with chlorines on it and lone pairs. So let's ask ourselves, what is the arrangement of these? So the nitrogen-hydrogen bonds are polar, being pulled towards the nitrogen. So it pushes in this direction. So this is going to give you an overall dipole moment towards the lone pair. So this is going to be polar. Because we can look at the vectors. So it matters, 1, is it a polar bond? 2, do the polar bonds push in the same direction or opposite directions? So let's look at carbon with 3 hydrogens and 1 chlorine. So the carbon-chlorine bonds has a polar bond, and that bond goes in this direction. And the carbon-hydrogen bonds are either nonpolar or borderline polar. And if they are borderline polar, the electrons are pushed towards the carbon center. So we can draw that as like a dotted line this way, if we wanted to, for a slightly polar bond. So this is also going to be a polar molecule based on the arrangement of the structures. So let's look at the carbon tetrachloride. So when we draw the same dipole moments, they're all going to push out from the carbon down all of these structures. These 4 chlorines are equivalently spaced. So this arrangement of 4 polar bonds is nonpolar. So to identify a polar molecule, you need to determine if the bond is polar using the electronegativity trend or the values. From there, you would look at the arrangements. And the greater the differential, the more polar the bond is. If the arrows point in the same direction, it's polar. If they don't, it's going to be nonpolar. So let's think about how polar molecules behave. So when ions are solvated by water, so if we have a sodium plus, we know based on previous videos that that's going to be solvated by the delta minus charge on a water molecule. And this delta minus is due to the polarity of this molecule. So what we see is that this is going to stabilize the ions, but it's also going to form an organized network. So polar molecules interact with one another. If instead we were to have a sodium ion surrounded by a series of compounds, a nonpolar compound, so in this case we will have liquid methane of CH4, this methane is not going to affect or stabilize the sodium ion in any way, shape, form, or fashion. So these are going to be non-interacting. So the polar behavior of water is going to allow the ions to be stabilized. We can start to think about how the polarity of a molecule or the molecules in groups is going to affect chemical reactions. And this is an important concept as we think of things as a chemist.